So this is what you should have filled out right now. Ugh, sorry, guys. My OneNote's been wonky all day. All right, so this is what you guys should have right now. If you need to cut the light out, you can, because I know it's light. So you should have the equation side of things filled out. All right, so we solve the equation by graphing. Now, we're also going to look at solving the inequality by graphing. So remember what I said yesterday. You're basically looking for if it's less than, if it's a less than or equal to symbol, you're looking for where the absolute value graph is below the other line. All right, and you use your x values as your point of intersection to figure out where they go. All right, or like where their start and stops are. If it's greater than, you're looking for where it's above the line. So if we're talking about less than, I'm going to say that less than, the absolute value graph is lower than the purple line right here. That's your less than. Whereas greater than, I'll do it in a different color. Greater than will be either over here and over here, because that's where our absolute value graph is above that purple line. All right. So if we solve this, how would I state the less than part? So look at the x values of your point of intersection. So -1 and 4. All right. How would I state where my less than is? How would I write that as a inequality where x is between? So guys, are my x values or my shading for less than, so the orange, is that falling between two numbers or on opposite sides of two different numbers? Between two numbers. So am I going to write two separate inequalities, or am I just going to write one big compound inequality? If I'm talking about between the compound. So I'm going to have something looking like this. So x with a less than or equal to on either side, because we have the less than or equal to. So what's my lowest x value? So what's my lowest point of intersection x value? Guys, x values right here. Which one's my lower one? -1. Which one's my higher one? 4. So we're saying the absolute value 2x minus 3 is less than or equal to 5 when x is between -1 and 4. Now, if we solve that normally, like algebraically, like we did yesterday, you would start out by writing this as a compound function. So you have the 2x minus 3 in the middle with a less than or equal to on either side. Now remember, the rightmost side is the positive version of your number, so the 5, or what you originally had. Whereas the leftmost is the opposite, so the negative. So it should be somewhere between -5 and +5. 2x minus 3 is. So remember, less than you make a compound inequality, greater than you make two separate. So then we just solve. So I add 3 to all three sides. This goes away. -2 is less than or equal to 2x, which is less than or equal to 8. And then divide by 2. So if I divide by 2, I'll get this answer. So whether you solve it graphically or algebraically, you should get the same answer. Is everyone following that? All right. Now, the greater than side of things. So if I'm talking greater than, all right, look at where the green shading is. How do you think I would write my answers as inequalities? So we're talking about in terms of x values. So am I going to have two separate inequalities, or am I going to have one compound inequality? So that means that it's between two numbers. What do you think? We would definitely have two separate. And remember, when we have two separate, that means we're going to have x is greater than something or x is less than something. All right. And it's our job to figure out which x values are where it's going to be greater than, which x values are going to be less than. So let's look at the graph. Again, we're still using our points of intersection, the x values of those points. So when x is -1, so right here, is my shading, so the green shading closest to the -1, are those x values on that graph less than -1 or greater than -1, where the green shading is? Less than. The x values are getting smaller. So from -1 over, our x values are getting smaller. So most likely, -1 is going to go with the less than symbol. Now, 4. So looking at when x is 4, is the shading where the x values are getting bigger or smaller in comparison to the 4? Bigger, because they're going to the right. So the shading's to the right of the 4, which means those x values are getting bigger. So that means x has to be greater than the 4. Does everyone understand how I did that? Yes, no, maybe, something? All right. So again, you're just looking specifically at the x values. So whenever you do this, you're only looking at the x-axis pretty much. We don't care about the y-axis. When it comes to stuff like this, when you're trying to solve equations by graphing, the x-axis is your friend. The y-axis is only there for actually making the graphs. After that, we don't care. All right? So almost think about it as just a singular, one-dimensional number line, like we've been doing yesterday. All right? If you look, if we were to graph this on a number line, the shading would go in the opposite directions, which makes sense, just like yesterday. And then if we did it as the less than part, the shading would be between the two, and that makes sense. So just like we talked about yesterday. So if we solve this algebraically, the absolute value is isolated, so I can go ahead and separate it. So remember, I told you to basically write the inequality again as is, just without the absolute value symbol. So 2x minus 3 is greater than 5. Then write the 2x minus 3 again, but flip the signs of both the inequality and the number. So less than -5. And then just solve each inequality individually. So if I solved, I would add 3 to both sides. This goes away. 2x is greater than 8. 2x is less than -2. Divide both sides by 2. X has to be greater than 4. And x has to be less than -1. So again, it's the exact same thing as what we originally got from the graph. So, does everyone understand how they can tell the difference, especially when they're looking at it from a graph standpoint? Does it kind of make sense? So again, if you're looking at a two-dimensional graph, so it has an x and y, after you graph both sides of the equal sign, don't worry about the y-axis anymore. It's irrelevant. We only care about what's going on the x-axis, all right? Because remember, your answers are written in terms of x. So after you finish graphing the equation, the y-axis is irrelevant at that point. And you're just going to pretend like that's just on one big number line and just the x-axis, all right? Does that make sense? So this is just a good summation of what we've been doing for the past 2 days. Also, the back side of it also has all the nice rules of how you separate everything and how you graph the inequalities. So those are very nice to have as well. So that's how you can use the back side. So there's no notes that we have to do on the back side either. All right. So it tells you how you separate. So especially down at the very bottom of your backside, it tells you how to separate your equation. So ax plus b equal to p, ax plus b equal to negative p, less than or equal to inequality. So negative p is less than ax plus b, or ax plus b is greater than p, ax plus b less than negative p, ax plus b greater than p. All right. So it actually tells you how you should separate them on your back of your graphic organizer. And guys, I'll let you use this on the test. So any questions on absolute value, anything? So solving equations, solving inequalities. All right. So breaking away completely from absolute value, look at your packet and turn to page, oh Lord. Yes. Yes. Turn to page. Someone look at their packet, and when they get to this page, tell me what page number that is. I can't remember off the top of my head. Landon. Yeah. It's page what? 28. So turn to page 28. So it should say 1.5 piecewise functions at the top. All right. So with piecewise functions, completely separate from absolute value functions, we're breaking away from absolute value functions. We're learning about piecewise, so it's a completely different type of function. Piecewise functions to me is one of the funkiest graphs you'll ever see, because it literally looks like puzzle pieces of different functions. So you could have like a linear function mixed with a quadratic function mixed with an exponential function all in one graph. But they start and stop at different x values. So technically it's all the same function, but it's different pieces. That's why it's called piecewise. It's literally like a jigsaw puzzle. So again, a piecewise function is a function in which it has more than one formula is used to define the output. Each formula has its own domain, and the domain of the function is the union of all the smaller domains. So the way this usually looks is that you would have whatever your formulas are. So in other words, whatever your equations are that describe parts of that function. Then you would have the domains for each value. So in other words, that we're basically saying that this part of the function is in play when x is within this range. All right, or it's within this interval. So this especially comes in handy when you're evaluating piecewise functions. So they look ugly, but they're actually not too bad. Now, again, when I say domain, what does that mean? What does domain typically refer to? Your x values. So remember, when I say domain, I'm talking about your x values. So to be honest, the little graphic up here is kind of hard to talk about. So we're just going to jump right into an example, because to me, it makes more sense, piecewise functions do, when you actually look at an example. All right. So for f of x, we have it equal to this piecewise function, and we're going to use it to evaluate. So the way you break this up is we're saying that this piece of function, so this linear function, is only in play or is only graphed when the x values are less than -2. So we can only use this function if the x values are less than -2. The x plus 8, we only see it on the graph between -2 and 3. And then 1/3 x plus 7, we only see it used when the x values are greater than or equal to 3. So basically, these are my domains, and they're telling me where on the graph these piecewise functions are at. All right. So, because let's see if I can remember how to do this in Desmos. I just want to show you what this looks like. And you don't have to do this. I just want to show you what it looks like. So if I made this into a graph, I would have y equals, what is it, x plus 8 is the first one? I do without the y equals. Let's do this. Y1 equal to x1 plus 8. For when x1 is nope, I can't remember how to do it in Desmos. You can't do it in the graph calculator either. But if we just Google what a piecewise function looks like, just so you guys can kind of get an idea of what they look like, because they're weird. Piecewise functions look something like this. Like, here's an example of a piecewise function. So here's an example of a piecewise function. Like, look at the graph. Like, it looks like we have a linear graph mixed with an absolute value graph mixed with a linear graph. The graph is literally in pieces, and they describe each part of the function between the different x values. All right. So, for example, the red part of the graph is only in play when x is less than -2. So, right here, all the x values are in play here. This absolute value part of the graph is only in play when the x values are between -2 and 3. So, from here to here, these are the x values. And the green part of the graph is only in play when x is greater than or equal to 3. So, the x value is greater than or equal to 3 is just that part of the equation. All right, so that's how piecewise is kind of broken apart. So when we're evaluating, the way I tell people to evaluate piecewise functions is figure out what x value you're evaluating at. Plug it into each individual domain. So for x into each individual domain. So plug it in literally for each of these x's. And ask yourself, does that number make this statement true? If the answer is yes, the connected equation is what you plug it in for x to evaluate. So that may not make sense, but what I mean by that is, for the first one, if I'm finding f of 2, what does that mean? I'm solving for when what? When x is equal to 2. So I'm going to plug the 2 in for each of these domains and see if it's true or not. So is it true that 2 is less than -2? Yes or no? So is 2 less than -2? No. Is -2 less than or equal to 2, which is less than 3? Is that true? So in other words, it's 2 between -2 and 3. Yes. And then just to double check the last one, is 2 greater than, so is 2 greater than or equal to 3? Is that true? Yes or no? No. So given that the middle domain is true, that means we're going to plug in this 2 into the x plus 8 because that's the domain that's connected, because that's the function that's connected to the domain -2 between -2 and 3. All right. So to evaluate this, I'm going to plug in 2 in for the x and x plus 8. So I get 2 plus 8, and it's 10. Kind of making a bit more sense now? Kind of, sort of, maybe? All right, let's try another one. So again, I'm evaluating when x is equal to -4 here. So we're going to do the exact same thing. I'm going to plug in -4 into all three of these domains and ask myself, are they true? So is -4 less than -2? Is that a true statement? So is it true that -4 is less than -2? Yes. Is it true that -2 is less than or equal to -4, which is less than 3? So is it true that -4 is between -2 and 3? No. And is it true that -4 is greater than or equal to 3? So is -4 greater than 3? No. So we're going to use the first function connected to this domain, which is 5x minus 3. So I'm going to plug the -4 in for x into 5x minus 3. So this would be 5 times -4 minus 3. So 5 times -4 is -20 minus 3. So that will be equal to -23. So guys, thumbs up if you're kind of understanding, or let's do it this way. So on a scale of 1 to 5, how are you feeling with this so far? So hold up one finger if you're good, if you're not great, 5 if you're, I can throw any problem at you, you'll get it. So on a scale of 1 to 5, how you feeling? Okay. All right, so let's do some more. So I want you guys to look at the next one. So we're finding when x is equal to 3. Without fully writing this one out, so writing out all the domains, which function up top do you think I'm going to use? The yellow, green, or blue? And remember, it's based off of whichever domain 3 fits into that makes that inequality true. So where do you think it will go? Blue. Why blue, Gavin? Right. Because if we're equal to 3, even though this one has 3 in it, it says it's less than 3, not equal to. This one has the equal to. So since 3 is greater than or equal to 3, that's a true statement, we're going to plug it into the blue function, which is 1/3 times 3 plus 7. And the original was 1/3 x plus 7. So if I evaluate it, 1/3 times 3 is just 1, plus 7 is 8. All right. And then the last one, f of 0. So again, we're finding when x is equal to 0. So we're going to do this kind of as a class. So let me ask you this. When x is equal to 0, I want you to hold up one finger if we're going to use the yellow function to evaluate, 2 fingers if we're going to use the green function to evaluate, and 3 fingers if we're going to use the blue function to evaluate for when x is 0. Ready? 1, 2, 3. Good. You should have used the green, or it's 2 fingers. So why are we, can someone raise their hand and tell me why we're using the green function? Why can we use the green function? Tomas. Right, because 0 is between -2 and 3. That's the only domain that 0 fits in. So that means we have to use the function connected to it, which is the x plus 8. So I'm going to plug in 0 in for x. So I have 0 plus 8, which is just equal to 8. So How you guys feeling on evaluating? So 1 finger up if you're like still completely lost, 5 fingers if I could throw a problem at you and you'd be able to answer it like that. How you feeling? Okay, so most of you are in the 3 to 5 range. That's pretty good. That's where I expect you to be. All right. So we're still going to do some more. Now, the 3 linear equations have y-intercepts. So if we broke apart those 3 linear equations, their y-intercepts would be -3, 8, and 7, respectively. So in order, the yellow function would be -3, the green function would have a y-intercept of 8, and the blue would be 7. Yet, a function can have only one y-intercept. So, which of these 3 numbers is the actual y-intercept of this piecewise function? And explain how you choose. So, let's kind of think about this. So, when we're talking about a y-intercept always has what? So, someone raise your hand and explain to me what a y-intercept is. Some properties of a y-intercept. Gotcha. As what? X value is equal to 0. The x value is always equal to 0. So we're looking for where x is equal to 0. So let's think about this. In the piecewise function, which equation is the only one that we can use that would fit when we have x equal to 0? The yellow, green, or blue? The green. Because if x is 0, 0 is between -2 and 3. So my y-intercept has to be, my y-intercept has to be 8 because that's the y-intercept of the middle function. Because that's the only part of the piecewise function where x equals 0 fits the domain. So my y-intercept is equal to 8 because x equals 0 fits the domain of -2 is less than or equal to x, which is less than 3. Of the function. All right. So it's based on wherever 0 fits in the domain. That's the y-intercept that you use. So if you graphed x plus 8 just by itself, you would have a y-intercept of 8. All right. So for this piecewise function, the y-intercept is wherever 0 as an x value fits the domain. That's the function that you would use to find the y-intercept. Does that make sense? All right, then there's average rate of change. And you guys may or may not remember this from Math 1. But average rate of change is just a formula. So to recap, the formula for average rate of change is y2 minus y1 over x2 minus x1. All right, so all that means is that if you're given 2 points, x1, y1, and x2, y2, you use them to essentially figure out the slope between those 2 points. All right? Or how fast they increased or decreased between the 2 points. So we always use the x values in the inequality that they gave us. So -3 and 9. All right, so I'm finding out on the bottom when x is equal to 9 minus -3. So we're going to use -3 as x1, 9 as x2. Now, we all know that on a graph, if you have an x value, there's always a corresponding y value. How do you think I'm going to find those y values for those 2 numbers? Using the piecewise function. So guys, wouldn't we just kind of do what we've been doing? Figure out which domain it fits and evaluate. That would give us the y value. Exactly. So we would figure out what f of 9 is equal to and what f of -3 is equal to. So for f of 9, which equation am I plugging it into? Up top. So where does 9, what domain does 9 fit into? Landon. Right. We would use the blue equation or the 1/3 x plus 7 because it's obvious that 9 is greater than or equal to 3. So we're going to plug in 9 into 1/3 times 9. What is it, plus 7 or minus 7? Plus 7. So if we evaluate it, we get 3 plus 7. And again, you guys can put this straight into your calculator. And that's equal to 10. So when x is 9, y is 10. And make sure you put them like in line with each other. Minus, what about -3? Which function would I use that fits the domain when x is equal to -3? The first one, because -3 is obviously less than -2. So we'll plug it into the first function. So this would be 5 times -3. What is it, plus 2? Right? Plus 3. Okay. So this would be -15 plus 3. Say it one more time. Oh, minus 3, Lord. So this would be equal to -18. So then we would have -18 up here. And then we just evaluate this expression. So remember, two negatives make a plus. So we have 10 plus 8, or 10 plus 18, which is 28, over 9 plus 3, which is 12. And make sure you simplify that fraction. So what would this fraction simplify down to? 7 over what? 3. Because both of them have a 4 in common, so we can divide the top and the bottom by 4 over 4, and we would get 7 over 3. And that would be my average rate of change between that interval. So essentially what that's saying is that between the x values of -3 and 9, our graph grows or increases at a rate of 7/3. Any questions on that? All right. Now comes the graphing side of it. So for number 2, we're just going to graph this piecewise function. Now, when it comes to graphing piecewise functions, you still got to know what the inequalities mean in terms of whether you have open circles or closed circles. Yes. Yeah. So what inequality symbols do I have to have if I have an open circle on a value? So if I have an open circle on a point, why would it be open? What inequality symbols would have been with it? We talked about this yesterday. Less than or greater than, which means a closed circle is less than or equal to, greater than or equal to. All right. So first things first, we're going to graph this function. So we're going to graph each of these individually. And again, I would just make a table of values. So the way I like to do this is, I would say this is x plus 4, which is the y's for x plus 4. And then this is x, and this is -3/2 x plus 9. All right. So these are going to be the points that I use to create it. Now, Your points should always start with your endpoints. So if there's only one endpoint, you just know that that's your either biggest or smallest x value that you use. If it's between two numbers, you use those two as an endpoint and fill in the in between. So for x plus 4, it says I'm between negative 2 and 2. So those are my endpoints for x. Now, based off of the inequality signs, so here and here, what type of circle would I have on top of negative 2, open or closed? Closed, because it's a greater, less than, or equal to. So this would be a closed circle. So I usually like to mark it next to it. What about for 2, open or closed? Closed. All right. Now we're going to fill in some other x values between negative 2 and 2. So you could say negative 1, 0, and 1. All right. Now we're going to find those corresponding y values. Now you could plug in each x value in for x in the function and evaluate, but you can always use Desmos as well. So if I have up Desmos, remember you can put in y equals x plus 4, hit the gear key, create a table, and there's my table of values. And lucky us, it's the exact one that we want. So when x is negative 2, I'm at 2. When x is negative 1, I'm at 3, 4, 5, and then 6. So that just came straight from basically copying this table. And then I'm going to graph these points over here. So I'm going to start by graphing my endpoints. So I'm going to have negative 2, 2. So I'm going to draw a big, fat, open circle or closed circle on it. So I'm going to make that point bigger than my others. And then 2 up to 6. So 1, 2, 3, 4, 5, 6. Put another closed circle on top of it. Now, my suggestion to you is don't draw the lines between the endpoints just yet, because you may not think that, depending on what type of function you have, that may not be the shape you're going for. So I would graph 1 or 2 other points that you came up with. So I'm going to graph all 3 that we came up with. So negative 1, 3, 0, 4, and 1, 5. So I'm going to graph those other 3 points, and I made them a little bit smaller than my 2 endpoints. And then I'm going to connect them. Now, you're not going to draw arrows ongoing. Why? Why would I not draw arrows like do this? Why would I not draw an arrow like this? Why can't I do that? Say it one more time. It doesn't keep going. We're only looking at that graph between negative 2 and 2. So we don't draw arrows because arrows implies it keeps going in whatever direction the arrow's going in. All right. Now let's do the second function. So my endpoints are at 2 and 6. Now, what type of circle would I have with the 2? Open or closed? Open, because we have a less than sign in front of it. So make a note that it's an open circle. What about 6? Open or closed? Closed. All right. Now, I'm going to list some points. We're not going to list all of the points between 2 and 6, just a couple. Usually 2 to 3. That's usually the sweet number. So I'm going to do, let's say, 1. Nope, not 1. That's obviously not between 2 and 6. I'm going to say 3, 4, and 5. All right. And then just like we did with the previous one, I'm going to use Desmos to generate my y values. So I have y equals, is it negative 3 halves or positive 3 halves? Negative 3 halves x, and then what's the last part of it? Plus what? 19. Then I'm going to generate a table. Plus 9. Easy fix. There we go. All right. And then I'm going to scroll down to where my x is 2, and I'm just going to add in my other x values. So 3, 4, 5, and 6. So, and I'm just going to copy down my y values given those x values. So I got 6, 4.5, 3, 1.5, and 0. And then I'm going to graph them. All right. So I'm first going to graph my endpoints. So I have 2 up to 6, which if you notice, it overlaps our other endpoint from the other equation. So I'm just going to draw an open circle around that for right now. And we'll talk about what that means in a second. Then at 6, 0, I'm going to draw a big old closed circle over it because we said it was closed. And then I'm going to graph my other points to the best of my ability. So we have 3, 4.5, so about right here. 4, 3, so right here. And then 5, 1.5, so about right here. And then I'm going to draw my line. Now, something to note. If you ever have if your two equations overlap, but one of them has an open circle, one of them has a closed circle. It's almost like rock, paper, scissors, how rock beats scissors. Closed circle beats open circle. So in other words, if one of them has a closed circle and the other one's open circle, but they're right on top of each other, all you need to do is keep that closed circle. So you still got the line going to it, but you don't have to draw the open circle. So closed circle beats open. And that's what that piecewise function would look like. Now, let's determine the range of the function. So range means what? So when we say range, what am I talking about? The y values. So remember, we want from the lowest y value to the highest y value. So what's my lowest y value? 0, which is right here. This is my lowest y value. Now, we're going to write this in interval notation. So would I use a bracket or a parenthesis to describe the 0? A bracket, because it's closed. Bracket means you had a closed circle. Parenthesis means you had an open. So we'd have bracket 0, comma. What's my highest y value? When y is 6. Now, I'm going to put 6, and then do I put a bracket or a parenthesis? Bracket, because it's a closed circle on top of that as well. So that's my range. Now, is the graph continuous or discontinuous? So continuous means that there's no breaks, no holes. Discontinuous means that there are breaks and holes. So what do you guys think? It would be continuous on the domain. All right. So I would say this is continuous because if you ran your pencil along it, there's no holes, there's no breaks, there's no open circles anywhere. It's pretty much a consistent, like you could run your pencil perfectly along the graph. Yes. Yeah. So any questions with any of this involving piecewise? So with piecewise, all I'm going to expect you to do is either name some domains and ranges and evaluate piecewise. That's really all I expect you guys to do. And occasionally you're going to have to graph one. But that's literally all I expect you guys to do. So if you can evaluate a piecewise function, you're fine. All right. So for the rest of class, your packet work is page, what's the next page? 29? So page 29 is your packet work for 1.5. And then you're working on the same delta math from yesterday. So the 1.4 through 1.6 delta math. You should now be able to do any of the ones that say anything piecewise functions. All right. So you should, on that delta math, you should be able to do anything absolute value. You should be able to do anything piecewise. You guys have a solid 50 minutes until class ends. So you can get plenty of work done. All right. So go ahead and get started. Yes.